Just going to give everybody a few minutes to jump on. I kind of sent out a real quick little story text earlier about me doing automation tonight. So I'm hoping I gave an early enough warning to where most people could kind of see what the topic was. So like I said, we just want to give everybody just a couple of minutes to sign on. Made up this little paper here, so we're going to be covering just some automation principles. Just kind of talking about automation in general. I want to give a quick rundown of just some key things that to be aware of. I know the interesting thing about it is a lot of things in automation translate over into just a lot of our basic controls. And the thing, in addition to that, almost all of the controllers going into a lot of equipment now, especially commercially, are DDC controllers, which DDC is a form of automation. So we'll get into that in depth here in a minute. I want to give everybody about 30 more seconds, so just hang tight with me, guys. So anyway, good week so far. Babies any day now, so still waiting on that. It's been a busy week, had a lot going on, but it's been a good week. It's been a real good week. I know, keep going to supply houses. I keep telling everybody you're not going to see me for a couple of weeks, and I keep showing back up anyway. So like I said a few minutes ago, we'll go ahead and get started here. Give everybody a couple of minutes, so we'll go ahead and kick it off. So today is going to be some automation principles. We're going to be talking about some things about automation. So one thing I want to get kind of clear that really kind of gets sketchy for a lot of guys is the difference between a automation. Yeah, good one, Rookie. I got you. Is the difference between solid state devices and DDC devices. Okay, so if you don't know, DDC is direct digital control, and so a big difference between solid state and DDC is the actual logic of the controller itself. So solid state is any regular control board, especially you see it on a lot of your older style systems. A lot of your older heat pumps are solid state devices, which means they don't have a legitimate microprocessor. There's nothing in there legitimately processing a series of inputs and outputs or anything else to control what it does, where it goes. It is strictly a board that if it has a signal come in from something, whatever, whether it be your Y signal, your O signal, whatever it is, then that board just triggers a series of relays because of that signal. And that's as deep as a solid state's logic really goes. There is no in-depth logic. There's no real communication. It's just a real basic series of input voltages that result in output voltages. That's it. Well, when you start getting into DDC, which again means direct digital control, which is so a thermostat. Let's start there, Rookie. A thermostat would be a DDC type device, because a thermostat nowadays, not originally, but nowadays, your typical thermostat, like a Nest, it has a logic actually built into it. It's got a lot of logic actually, and so for what it is. And so because of that logic circuit, it's got actual microprocessors in there that run it. It is a DDC device when you get really technical about it. Just that's what it is. So that's an example we could look at. If you do any commercial work and you see the controllers, in mechanical rooms that you work on, or even a prime example is these new Daikin Rebel package units are coming out with the Microtech controllers. Those systems, that Microtech is a DDC controller. It has legitimate logic that it's looking to. And so I just want to make that distinction very clear between the DDC controller and a solid state. They are two different things. They serve two different purposes. Okay. So, actual automation. One thing great about automation is you get a lot greater control of what's actually happening, because you have some very in-depth algorithms that can be plugged in that can very critique control of that system. You know, chillers have been using DDC logic for years and years. DDC logic itself has been around for many decades. It's just now getting into a lot of your smaller systems. A lot of your residential style systems are starting to see a lot of that logic, where for many years it never got introduced to that portion of the trade, but now it is. And so it just, at the end of the day, it's got a series of temperature sensors, and you can even do pressure sensors of various types that allow that system to know what it should be doing, when it should be. And I want to kind of talk about that a little bit. So I wrote up a little page here. I'm hoping everybody can see it pretty good. So we talk about logic. What is logic itself? So the actual logic, the most common logic I run into personally in most of the systems, I see the most common system I see is Distech, Honeywell, and Johnson. Those are the most common I run into. My company also services those three brands. There are several others that we have in our area here in Austin. At Snyder as another one. Reliable Controls is another. There's two main types of logics that you'll run into. There's actual block logic. That may not be the official term, but that's what I've come to know it as. It's block logic, and then you've got actual script logic. So block logic, it looks kind of like this. If you ever pulled up the logic sheet inside of a DDC control system, or on the front end where the computer is, where you can get on and see everything, it looks something very similar to this. Now, granted, it may be a whole page full of blocks and different points, but it's going to start here one block, and let's say this is a fire or engage relay K3, which turns this contactor on. Well, in order for it to engage that contactor, it has to see this point. That's where you have a and or scenario. So with a block logic, you deal with and ors. Okay, so you have to have this point and this point in order to get the wanted result, or you have to have this point or this point to get this wanted result, and as a form of control. So an example of that would be if you had like a freeze stat. Zoom out, please. Okay, is that a little bit better? Now we'll cover all this in the video as we go. Hopefully you can see that a little bit better. Anyway, an example would be if you had a high and low pressure switch on a system. You know, those would be technically two and or points that the controller could pull into and actually see. Okay, so I've got this safety is closed, this safety is closed, and so both of those have to be closed. So I have to have and to get this my compressor contactor to engage. All right, so that's kind of the basic thought process behind the and or logic. And this is the most common style. That each brand has their own way of doing it, but they all essentially end up doing the kind of same thing. They've got the same basic format, the same idea, the same mentality. It may have a different look on the actual computer itself, but it's going to do the same function. The other style I said earlier was the script. So if you know computer programming at all, you'll know that a script is the actual line-by-line code written into that computer's logic. You know, it works in ones and zeros, right? Well, some programs out there are actually script-written programs, which means you have to be able to go in and write most of them are pretty basic script lines into the coding to actually get the results that you want to get the control. Now, at the end of the day, you still have this same and/or process that happens. It's just instead of having it in a block format, it'll be in a script format, just like you're sitting there reading computer code on your computer. So that's the two main types that you'll run into is block and script. And unless you're actually getting into the programming side of the system, you may never see this stuff. But it's important to understand how that controller is looking at its different components and what it's going to take to cause it to fire. You know, another example of this and/or it would be a thermostat and safety switches. You know, that's just another example you could throw out there. So you have to have the thermostat actually calling and the safety switches closed in order to bring in your contactor. Okay, there's a million scenarios you could draw up with this, and they get very complex very quickly. Moving on. So what trips a lot of guys up is when you actually look at a DDC controller, you'll see like AIs, AOs, DI, DO, or it may be a BI, a BO, or even a UI and UO. All of those are a description of the type of input or output that it is. So the I and the O at the end just tells you is it an input, meaning it's giving a signal into that controller, or is it if it's an O, then it's an output leaving the controller. Now let's make something very clear. Digital and binary are the same thing. They're literally on or off, 0 or 100. There's no in between. There's no middle ground. There's nothing. It is on or off. So that would be a basic signal for that would be a relay inside the controller closing, bringing on the contactor for that component, whether it be a blower motor, compressor, whatever. That would be a binary output at that point. A binary input would be a low pressure switch, a high pressure switch. If we're dealing with a furnace of any kind, you could throw in high limits. Anything that is either off or on, any switch that opens or closes, or a coil. If you're needing to energize a coil, that is a binary device. Contactors, relays, safety switches in general. Fan proving switches if you deal with a lot of VAV equipment or fan power boxes. All those are binary devices. They're going to be hooked up to the board on the DOs or BOs depending on what your board is. And really, the only thing that makes a difference here is the brand. A lot of your brands, the most common that I run into is digital, or it says D instead of binary. And so, like I said, it doesn't matter which it says, D or B. It means the same exact thing. Don't let that trip you up. Moving on to analog. Now, analog can be a range of readings. So I have written down here 0 to 100%. That is an analog device. So a prime example is a thermistor or a thermocouple or a transducer. All those are analog devices. They have a 0 to 100. Anywhere in between it can be. And so depending on what that value is and what the logic, and so that's where it's tied into the logic. So written in the logic, it knows that if I have you say 500 ohms on that thermistor, I'm just throwing a number out there. If I have 500 ohms on that thermistor, and that means I'm at 20 degrees Fahrenheit, right? Or a 10,000 K resistor is, I think, pretty common. And so it's 10,000 ohms, I think, at 77 degrees, or depending on your type. And there's different types of thermistors out there. And so if you don't know a thermistor, we all deal with them every day at this point in the trade. They're common items. But they just vary in resistance depending on temperature. They are temperature sensitive. I'm trying to keep this as still as I can, guys. They are temperature sensitive, so depending on what the temperature is around the thermistor or whatever it's coming in contact with, you know, the logic in the controller knows that that resistance equals this temperature. And, you know, sometimes we do have to calibrate that. You know, there's a number of things we have to do, but that is what analog means. So if you see a AI or a AO, that's what it's looking for. Now, the thermistor and a transducer, those are going to be AIs. I mean, they're analog inputs, okay? So what an AO at that point, so the O meaning output, a analog output would be if you have an actuator, okay? A perfect example, everyone I'm sure is familiar with, is Linux package units. They've got their Prodigy controllers in there. I had to think about it. In there now, or they have had for some time. And if you have a outside error package on that Prodigy system, then you know, it's going to have a analog output going to a actuator to open and close the outdoor air damper. Okay, that's an example of an analog output that you could run into. The same thing for if you do a lot more heavy commercial, a VFD, variable frequency drive, controlling a motor of some kind. You know, we give a voltage signal or a Mili-Amp signal to that VFD, telling it, okay, if you're at 5 volts DC input coming into that VFD, I want to run at 50%, right? Or be 30 hertz for that, as far as that VFD is concerned. You know, and so that's a whole other topic. But anyway, that is your analog output. So any kind of a varying output, it could be to a different controller, it could be to a number of different things. That is what it would be. Another example of a analog input, I had a chiller plant that they had a aftermarket temperature sensor on the condenser water loop. And this was before the plant had been converted to a centralized DDC system. It was still a very old school setup prior to that. Anyway, what they were doing, though, for this VFD to control the tower fan, was the thermistor actually had a little processor board connected to it that converted the temperature itself into a 0 to 10 volt DC signal. And so we would then run that 0 to 10 volts DC from the sensor to the drive, and then I had to program into the drive that when it sees this voltage DC at this input, and that means that I have that's my temperature is X inside my condenser water loop. So those are examples of some inputs and outputs, and yes, VFDs have DDC logic and technology built into them. DDC is a very wide branded thing. A lot of times we like to call DDC EMS, BAS, any of those other acronyms. Those are just energy management systems, building management systems. That's all they are, but they all mean the same thing. They're all talking about a DDC system. Okay, DDC is, at the end of the day, the core that everything is controlled by. That's just a terminology thing. Again, they all mean the same thing, kind of like binary and digital. They mean the same thing. So we talked about binary and digital. Those are off and on. We talked about analog, that's 0 to 100%, whether it be input, output. Let's talk about universal. Universal is kind of what it sounds like. It'll have a U, so instead of an A or a D on that terminal point, it'll have a U instead. And so if it's a universal point, that means that controller could be programmed, and it depends on how the logic is written, could be programmed to do an analog signal or a digital signal. It could be either or. And so that just, again, depends on what they tell that particular point to do. Now, here's something I'm going to throw at you just to keep in mind. You can turn an analog output into a binary output. Okay, and the way you do that, and it has to be programmed into the logic, but in the logic, depending on what point, so if you need to turn something off or on, you would have to tell it to, okay, so you're either going to be 0% or you're going to be 100%. Don't give a range in between. And you can do that in the logic. You can tell your controller, your automation guy can, that, you know, if I don't want any signal coming out, it's going to be 0%. The moment I want signal, I'm not going to increase from 0 to 100. I'm going to go straight from 0 to 100% output out of that analog point. And that is how and you can run into that sometimes too. That is how some controllers, you know, if they run out of points on their controller, they will convert an analog into a digital signal to still get the same effect. And again, that's kind of how universal inputs and outputs work as well. And so they take kind of a similar format, but they are actually more structured to do legitimate digital output, not just kind of make it work like an analog can. It can be a little bit different scenario. A big thing about digital and binary inputs and outputs per se, not inputs but outputs, is the outputs themselves are typically an actual relay. So there'll be a legitimate relay built into the controller that controls the output signal going out. So the controller fires that relay and closes it. All right, I kind of sitting here now, I kind of wish I had a controller in front of me. I could show you a little bit better, but that's okay. So those are your three main inputs and outputs you're going to run into. The signals themselves are going to be down here at the very bottom. You can see you can either run into a 0 to 10 volt DC on your analogs. You can see there's actually 0 to 10 volts and there's 2 to 10 volts depending on your system and what you're doing with it. There's also a 4 to 20 Mili-Amp. Now, for those of you who don't know, the only way you are able to read a Mili-Amp signal is to put your meter in series with the control circuit. Okay? You need to verify that your meter actually reads milliamps in the first place. But you know, so a lot of your actuators, you could have a Mili-Amp control system just as well as you could have a 0 to 10 volt DC. So instead of sending 0 to 10 volts to that VFD or that actuator, either or, to control it, it could be a 4 to 20 Mili-Amp. And so, like I said, if it is a Mili-Amp system and you want to know, okay, how many milliamps am I giving that controller, or that component, I should say, you'll have to unwire the signal wire and then wire your meter leads into it and run the signal through your meter so that you can actually see what that signal is. So just keep that in mind. And so a 0 to 10 volt DC, that could be a binary or a analog signal. You know, it could be 0 to 10 or it could be 0 or 10 volts depending on the setup. Same thing with 0 to 5. So a lot of times the 0 to 5 is most frequently seen in actual sensors such as transducers. Transducers use a 0 to 5 volts DC for their signal. So they have to have 5 volts DC going to them, and then depending on what pressure it is that they're reading, whether it's air pressure or whether it's refrigerant pressure, whatever the pressure may be, it's going to output that 0 to 5 accordingly, and then the controller can receive that 0 to 5 back from the transducer to know, okay, this is my pressure. So that's an example of where you'd see a 0 to 5. And then obviously ohms is going to be another analog input at that point. It's not going to be an output, but it can be an analog input. Again, thermistors are the most common to see for ohms themselves. So this was just a basic breakdown of automation systems. We started, from the logic to the different points to the types of control signals. Now, keep in mind, guys, these aren't all of the signals that can be received, but for the most part, 98% of the systems you're ever going to run into out there, if not 100, depending on how much exposure you get, are going to be somewhere on this page. They're going to fit these parameters. They're going to fit everything we've talked about. And so when you start looking at controllers, start looking at these different AOs, AIs, DOs, DIs, or UOs and UIs to know what it is that that could be running off of that point. And that really can help go a long way when you're trying to trace things out, or even if you're looking at it and you're trying to figure out, okay, how is this supposed to work, or how is it supposed to do what it is it's doing. By knowing if it is a input or output can really help you determine what component could be hooked up there, whether it be a thermistor, a contactor, a relay, whatever. Anyway, guys, if we have any final questions on this or anything come to mind, feel free to reach out. Put that up there so everybody can see it real good. I will be getting this video posted to YouTube, and I'll probably split it up, and I'll probably post it in my IGTV feed as well. So anyway, guys, I appreciate it. I'll try to. So I'm still figuring out exactly what all I'm going to do with the storyline. I'll try to give a little more heads up than I did tonight. I think I only gave like 30 minutes on what tonight's topic's going to be. I wanted to try to give y'all at least a couple hours going forward. So I do apologize if it was a little short notice for you guys. Here we go. So we got a question that says, how would you determine the difference between a 0 to 10 volt DC or a 4 to 10 or 4 to 20 milliamp? So the easiest way is to actually just physically check it. So put your meter to 0 to volts DC. That's where I start. I start at volts DC. I put my meter there, and I'll check that signal point to a ground source. So anytime you're dealing with DC voltage, just go to a ground source somewhere, but go to that signal point to ground. And if I don't have a DC voltage in there somewhere, a lot of times the 4 to 20 a lot of times it'll come up as a higher voltage. Like it'll have a 15, 20, 24 volts DC depending on the system. And so if I see that type of voltage feedback, or if I don't see any kind of voltage feedback at all, my next step is I'll put my meter in line and see if I get a milliamp signal that way. So like I said, that's usually what I do. If I don't know at all going into it, that's the procedure I go through to try to determine it. I start with checking the voltage, see what voltage readings I get, and then from there, if I don't get anything, or if I'm getting a really high, when I say high, like 24 volts DC or something going through there, or 20 volts DC, my next step's going to be to go to milliamps and put my meter in line. Really good question. I didn't actually cover that, so I appreciate that. So anyway, guys, if you have any more questions, please throw them out. Otherwise, I'm going to go ahead and wrap it up. I appreciate you guys. This has been a really fun journey for just this whole Instagram process. I've only been doing it since January, but I've really loved y'all's interaction. I love getting to do this. This is a huge passion for me. What's another huge passion for me is making sure you're spending time with your families, guys. I try to hit it as much as I can without just completely being flooded out. But your families need you at home. Your kids need you at home. Put that time in. Go play dolls with them, or go throw the baseball or football, or You know, help them with their homework, help them study. Do whatever you can to be an active member of whatever it is they've got going on. And then your spouse, just be there with your spouse, put that time in. You know, when you get home, put work away as best you can. I struggle with it. You know, that's an everyday struggle for me. I'll admit I'm a workaholic, and I struggle with just putting my work aside and coming home and being home. But it's something I'm working on every day. My wife helps hold me accountable to that, and I'm really appreciative for her for that. And you know, it takes a daily effort, guys. It takes a daily conscious decision to just have that life choice. So please put time in with your families. If you don't have a strong or good, happy home at home, you know, you're going to struggle out in the field. I've experienced that myself. I experienced that with my coworkers. I'm very set in the fact that that's just a reality of life. You got to have a good, strong home structure built, and if you do, you're going to see that reflect in your career and what you're able to do. They go hand in hand, guys. Anyway, appreciate it. Stay safe out there. I know we're wrapping up summer, so yippee. I'm looking forward to not as much heat myself, and I'll catch y'all next time. Baby update, maybe this weekend. Who knows? We're still waiting. But as soon as little Abigail gets here, I'll let you guys know, and I will be taking 2 weeks off for her and spending the first 2 weeks of life with her. So I'm taking everything. My Instagram, my work, all of it, taking a 2-week break. So, but I'll let you guys know when that happens. That way you're not caught off guard. Appreciate it. See y'all later.